So in the schedule, if you're following along with where we should be in the course right now, it talks about weathering and erosion as the next topics. And in fact, I'm going to skip over the weathering for the time being, except in a little tiny bit. And so we'll talk a little bit about it, but not much. And so we're going to move on with sediments and sedimentary rocks and how they get eroded, really. So just to give you a little bit of a background understanding first, you guys have already learned what Bowen's reaction series is. Bowen's reaction series says there's a systematic way in which silicate minerals will crystallize out of a magma, and it goes from the ultramafic to the mafic to the intermediate to the felsic at the very bottom, right? And so that's as temperature cools, right? So you form the simplest ones first, then you form the most complex minerals at the very end, or the very lowest temperatures in Bowen's reaction series. As it turns out, that's exactly the opposite with which things will actually weather. And so they have a series called the Gold-Rich series in geology, which is the way that minerals will convert to other minerals. And so which minerals degrade the most rapidly? And so the minerals that tend to degrade the most rapidly would include the ultramafic minerals first, and then the mafic minerals second, and then the intermediates, and of course the felsic last. So what it means is those ultramafic minerals become clays. The mafic minerals will then become clays, and then eventually you get into the rest of these sort of minerals, so the plagioclases and all that sort of material. They turn into clay. That is the ultimate destination for every one of those silicate minerals except for quartz. And quartz has a really long residence time. It's very stable. It has a hardness of 7, so it doesn't degrade very easily. And it's made out of a very complex, very tightly packed SiO2, so it's very simple. It doesn't have any cleavage, as you know, as well, so it's not easy to break it apart. So in fact, quartz is the survivor mineral, as it turns out. So the survivor mineral being the one that lasts the longest in the sedimentary environments. And this will make a lot of sense to many of you because maybe you're familiar with sandstone. Well, sandstones had to be derived from igneous rocks at some point. And so what you really see with igneous rocks is they deliver all these products, and most of them will turn to clays, and of course the sand just stays sand. So the quartz will just stay sand. So that's kind of it for the beginning of this, and so that tells you a little bit about weathering, at least the weathering products. Those are the products that get derived from weathering igneous or metamorphic rocks mostly. So that's what you get. And so when you weather these things, they become sand and clay particles. And so we're going to talk more about sedimentary rocks next. And so erosion and weathering are related to one another, and they're very commonly put into the same sort of chapter, I guess you could say, in introductory geology books, but they're very different from one another. So if weathering is actually the degradation of minerals and their crystalline structure, the erosion is actually the removal of it. And so you can actually wash things away. So once it becomes a clay, you can transport it and easily take that degraded particle and move it somewhere else into a depositional environment. And so that part is called erosion. So erosion is the physical breaking down, the physical movement of those rocks and taking them away. And so both of those aspects are important for delivering some sedimentary particles. You have to be able to break things apart. When we do it chemically, that's going to be called weathering. When we do it through erosion, and so we can do it through like the physical weathering of things, and when we do that, we can freeze and thaw it and things like that and break things apart. So that's kind of where we're going next. So we're going to make sedimentary rocks next. So we're going to go on and talk a little bit about sedimentary rocks next. And so I wanted to lead this off with a picture of a quarry. Now this quarry is just across the state line into Missouri, and it serves people both in northern Arkansas, northwestern Arkansas, and southwestern Missouri. This is at a place called Bella Vista, so it's the Bella Vista Quarry, and really extraordinary rock succession here. What you see at the very bottom, if you look very closely at the bottom of this quarry, there's a black rock down there. It's a black rock that's actually shale. It's a sedimentary rock. It is a rock that's named after the city of Chattanooga, so the Chattanooga Shale is at the very bottom of this quarry. Other folks have named that shale, they call it the Knoll Shale. So if you're familiar where Knoll, Missouri is, if you know where Knoll, Missouri is, it's named after the city of Knoll as well. And it's so dense, you don't expect this out of a shale, but it's so dense that they can put the basement or the bottom of a quarry in that shale. It's so resistant to weathering. But above that, you get this huge succession of both limestone and a little bit of siltstone and a lot of chert. And so this quarry has an exceptional amount of chert. And if I were to go through the rock units here, what you see here is the Chattanooga Shale at the very bottom. There's a very thin sandstone over the top of that, not more than like an inch or two thick. That's called the Bachelor Formation. Above that, you get the Compton limestone. Compton limestone is the lowermost part, well, actually the Bachelor and the Compton, and the rock unit above that are all the lowermost part of the Mississippian strata in southwestern Missouri here. And so above that, then you get the Pearson limestone, you get the Reed Spring formation above that, and then you get the Elsie formation above that. And so that's that entire rock succession. We have 5 different units or 6 different units that are named just in this one locale, and you can see them all, at least part of the upper one exposed there and the very topmost part of the Chattanooga Shale. So why did they put a quarry there? Why do you need these rocks? Well, in modern societies, in a very urban sort of setting, you guys are familiar with this, you have to have concrete in order to build a city. It builds the streets, it builds the buildings, it builds the foundations of houses, and it is the epitome. Every business that's out here has to, any brick and mortar we call it, right? So that's the mortar right here that comes from these sedimentary rocks. Even the brick comes from sedimentary rocks if you think about it. So these rocks were mined specifically in this case for building Interstate 49. So Interstate 49 runs all the way from Fort Smith, Arkansas, roughly, all the way north to Kansas City now. That's old Highway 71. They built Interstate 49. They had to have materials to build that highway. And so everything that we have on this planet, every consumer good has to be mined from the earth, and this is one of those materials right here. Quarries are so important. And for me as a geologist, they're so special because I get to see what the rocks are there and understand what I've seen in different places. And for me, it's a puzzle that you can put together and say, oh, okay, I know what's going on here. I know what's going on over here. And how do they fit together? So as a geologist, I'm trying to figure out the timing for when these things were deposited. Now, that's the interesting things about these rocks. Those are sedimentary rocks. They're limestone. Limestone generally accumulates between 30 degrees north or 30 degrees south latitude. So equatorial sort of zone. And we call that a tropical setting. And today we see rocks like this being made, being deposited in places like the Bahamas, in the Persian Gulf, in the Caribbean. So it's really interesting. It's mind-boggling to think that the Ozarks were once like the Bahamas. And yeah, it was. It was like that because we had high temperatures. We had the deposition of these carbonate minerals from mud and from other living organisms. So like the state fossil of Missouri is a crinoid, and that's a sedimentary particle. It's something that's made out of calcite. And so these calcite rocks, they're going to be forming the major part. Calcite minerals will form the major part of what we call limestone. And so limestone is sedimentary rock. Chert also a sedimentary rock. Chert is SiO2, right? So silica and oxygen, right? So that is a whole series of silica tetrahedra that are smashed together or compacted, if you will. And they're usually chemical in the sense that they will take and replace things. So I like to think about chert a lot like I think about petrified wood, because, petrified wood, it's wood. Yeah, you can see like the rings on a tree. You can see the bark sometimes. But in fact, it didn't grow with all that silica in there. The silica had to come in and replace the cellular structure. And that's the same way that in chert we have silica particles as little tiny dissolved particles in groundwater that will move that silica in and it'll replace things. And in this case, it's replaced the limestone that's there. And so chert and limestone are like this. And chert and dolomite are like this as well. And limestone and dolomite are like this as well. So the three things that tend to go together. And in this case, they're all in a tropical sort of setting. Really fascinating. The black shale, the Chattanooga shale here, however, is a different setting. It's when we had a massive time of global warming 400 million years ago. And it pretty much killed everything. One of Earth's 5 major extinctions is recorded in that rock unit. And it's called the Franian-Fomanian extinction. There's actually 2 of them then. Those 2 extinction events are among the big 5, and it was probably related to the chemistry of the oceans back then. So the chemistry of the oceans very acidic, so it wasn't a good time for limestone creating organisms to be around because they would dissolve in the seawater. And so that's the story of the succession right here, and it's absolutely beautiful too. When you look at the strata, it's beautiful. When you look at and understand the story that these rocks are telling you, it's a fascinating one. So geologists, sedimentologists, and stratigraphers study layered sedimentary rock, like me. This is my specialty. It's not volcanoes, no matter what you think. I loved volcanoes. I loved telling you what I knew about volcanoes, but in fact, this is my passion. This is my life's work, in fact, right here. Is looking at the layers of sedimentary rock and looking at limestones in particular. That's my specialty. So, yeah, these rocks are really astonishing. It's amazing the story that they tell. And we're still working on that. You know, it's like the rocks are there and they've recorded what their history is, but we have to figure out how to interpret it for them and to give it to other people so that they will understand how important they are. And so the limestones in this case, they turn it into aggregate. It's a product that gets mixed with cement, Portland cement, and they make a product called concrete. And so aggregate and Portland cement equals concrete. And so that's the importance of these rocks. Now, chert is not what you typically want to have in a concrete, because chert, when it's a piece of aggregate, we're talking a gravel-sized chunk of angular rock, right? When they crush this rock down and you have a little bit of chert in there, very commonly when that is in a concrete, it'll cause what they call pop-outs. And so it's not the high-grade concrete like you get around Springfield. Springfield has some of the best concrete in the world, all because we don't have that much chert. And so this is pretty important, in fact. So it's a major resource for all of southwestern Missouri. And it's a major resource around the world. Let me put it that way as well. Sand and gravel and limestone are probably the 3 most important economic minerals in all of Earth because they're used in the construction trades. And so if you're going to build something, you need geology. And so, in fact, if you have a city anywhere on Earth, you want to have a limestone pretty close to it, because if you don't have a limestone close to it, you're going to have to ship it in or have it in rail cars in order to meet the needs of what that community is going to have as that community grows and expands. And so we're pretty well situated both for fresh water and for the concrete resources that we have here in southwestern Missouri. So that's kind of neat. So that is the McClinton, Anderson, Bella Vista Quarry right here. Really kind of a neat place. One of the other interesting things about these rocks is that in the Reed Springs here, you actually can smell gas leaking out of one wall of that quarry. Natural gas is escaping from the Chattanooga Shale because it's organic rich. It's actually a petroleum source rock. Now, most people think that it's not mature, and so it doesn't generate oil or anything like that. But there's a lot of natural gas that gets generated. So much so, in fact, that some local folks, when they drilled their water wells around here, they were able to tap into that natural gas coming in, and they were able to heat their homes for a short period of time using the natural gas out of the Chattanooga Shale. So kind of neat. It's not deeply buried enough to make it a resource that is exploitable. But there are places where you could probably down in the Arkansas River Valley. And it's certainly the petroleum resource rock for much of northern Oklahoma and southern Kansas as well. So the oils that come out of that rock, they find in a limestone play, actually called the Mississippi Lime, southern Kansas, northern Oklahoma. And so it's a very important energy resource in that situation. Here we have the surface area where you can go, you can investigate it, and in fact, that's what I do. So very neat rocks. Okay, I'll move on here. Sedimentary rocks are made out of sediments, right? And why they're important. Okay, so they're important both for the economic value that they have and for the energy resources. They also are host to mineral resources as well. So sedimentary rocks will host some mineral resources like the lead and zinc. Okay, so in Joplin, that's the host rock for lead and zinc. In the Viburnum Trend in southeastern Missouri, that's the host rock for these sedimentary mineral accumulations, heavy metals that will accumulate in sedimentary rocks. So pretty important in both of those aspects. When we look at sedimentary rocks, one of the things we like to do in geology, of course, is to classify things, because if you can classify them, we can try to figure out what they are. So we try to come up with how do they come to be formed, and so that's why this is important. And so sedimentary rocks, we usually break them into three parts. Those three parts would be detrital sedimentary rocks, chemical sedimentary rocks, and then organic accumulations. The detrital sedimentary rocks are really important when it comes to things like shales, siltstone, sandstone, conglomerate, and breccia. And so breccia can be a lot of different things, but a lot of breccias are actually detrital based. And so you have to break the rocks apart essentially when you form a breccia. We'll talk about detrital rocks in a little bit more detail. Chemical sedimentary rocks are a lot like the chert I was talking about. So the chert is actually a precipitate of silica and oxygen, right? So it's SiO2 that comes into the rocks, replaces the limestone, or replaces the cellular structure in things like petrified wood. And so that's a type of chemical sedimentary rock. We also lump into that another group of sedimentary rocks that may form at the Earth's surface in dry deserts and places like that. Gypsum, for instance, is an example of a chemical sedimentary rock. It actually evaporates, and so we call that group of rocks that evaporates the water and leaves behind the mineral accumulations behind. We call those evaporites. And then finally we get to the organic accumulations, and that would include things that were once fossiliferous, and so fossiliferous limestone would be considered organic. Now, as it turns out, these are not hard and fast categories, and so even though your teaching assistant in lab is going to say, well, this one's detrital, or this one is chemical, and this one's organic, and there are ones that bridge across that gap. So in fact, there are some carbonate rocks that in fact are detrital in origin. They may have formed through chemical processes, but then they became a detrital fragment. So for instance, ooids will be one of those sort of features. So OOIDS, ooids are sedimentary particles that would have been precipitated from ocean water, but they then behave like a sandstone. So they behave like a lightweight sandstone. So they get moved around by ocean currents. And they're forming in the oceans today, in fact. And if you recall, when I first began this course, I was talking about the Bahamas. And I said, there's rocks just like in the Bahamas out on the west side of Springfield. And I said, the Short Creek oolite crops out, and it's exposed in a road cut, in fact, at Bennett Street in Kansas Expressway. And you can actually see the little tiny, I hesitate to call them pellets. They're not really pellets, they're ooids. And so ooids would have rolled around on the sea floor and gathered layers and then accumulated in a large enough body that they became essentially cemented together just after they were exposed to like rainwater that would have eroded the top part of the limestone and would have precipitated in that limestone, made a cement that binds those sedimentary particles all together. And so when we come to detrital sedimentary rocks, it's going to be very important for us to identify the difference between what's a cement and what we call matrix. What is the material that's surrounding the grains that are in that rock? And so we don't call them crystals anymore because they're not crystals now. but they are grains instead. So if they're like about the size of a sand grain or something like that's where the term comes from. They're about the size of a seed, if you will. And so we call those things grains. If they're larger than 2 millimeters, we're going to call them clasts. And so they may be a bioclast, they may be other sorts of clasts, intraclast. There's all sorts of different names that we use, but grains and clasts are going to be two of the important words that we use in describing sedimentary rocks. Okay, so as we go into this, the chemical precipitates we talked about organic accumulations. Coal would fall into the latter category as well. Okay, so the next slide gives you some of the background on what we just talked about, the physical and chemical weathering and the breakdown of igneous rocks. That's called weathering. The erosion is actually the removal of that material, whether it's by wind or water in the form of streams, or maybe it could also be glaciers. Glaciers will erode sedimentary rock or igneous rock as well. And so those are all forms of different types of erosion. And then eventually you can even get into the mass wasting. So mass wasting is going to be one of the topics that we cover later on in the semester as well. I'll talk about soils later on because we use soils more as a resource than we use as a, to explain how the clays actually got there in the upper part of the rock column at any given locality. And we'll talk essentially in this project, in this presentation, we're going to talk about the transportation and the erosion of these this accumulations of detrital material, how they accumulate in different depositional settings, and then how they just came to be. And in many ways, these rocks are really kind of inspirational. So the sedimentary rocks form the canvas over which 70% of the earth is covered by sedimentary rocks or sediments. And so they also, if you go to any national park, practically any national park, they all have sedimentary rocks in them. So it's kind of cool that way. So what you see in this image right here is a painting it's a view that inspired the painter Thomas Moran. Now he belonged to an art school. They call them the Hudson Valley Art School, the Hudson River School of Artists, and that was back in the mid 1800s, late 1800s. And they tried to paint what they felt was capturing the spirit of America and showing it to the people who lived in Europe. And so people in Europe did not understand. Of course, this is pre-photographs, some of the stuff like 1840s and 1850s, pre-photographs. And so Thomas Moran, he went out and he painted the Grand Canyon because he couldn't take a photograph of it. Well, Ansel Adams went around and changed that. He took photographs of all these places, all these great national parks. So with the Colorado River, it cuts through these sedimentary rocks and exposes them all. Well, when it cuts through those rocks, that is stream erosion. The Colorado River is removing all that sedimentary rock. And in fact, it's called the Colorado River because it is the color red, or it's usually brown, but all those sediments form the particles that are carried by that river, and those sediments get carried off into Lake Mead, where they then accumulate in Lake Mead. Originally, they would have accumulated far downstream and began filling in the Gulf of Cortez between Baja California and the mainland part of Mexico. So with this case, these are sedimentary rocks, mostly sedimentary rocks at the very top up here. That's a limestone. Below that, you get some red sandstones, and then you get the red wall limestone below that. It's red because the red rocks above it have stained the rocks below, that reddish color. And then below that, you get some older rocks, and so this cuts into these rocks. Most of these rocks, not all of them, but most of them were deposited in ancient oceans. So even the rocks at the very top were deposited in ancient oceans. It's a limestone. Most limestones accumulate in ancient ocean rocks. And so you can tell that because they have fossils in them. And so the fossils are a clue. It's like this would have been a marine rock. And so you see things like, well, maybe some trilobites actually. You can get some trilobites in the Kaibab limestone, which is at the top of this succession. They're not real common. but you get ammonites and some other types of sea creatures. You can get actually forams, little tiny single-celled organisms that made their skeletons out of calcite as well. The sandstones below that, actually, some of those are actually non-marine, but then when you get deeper in the canyon, there's some other limestones that crop out. The red wall is a marine rock unit. There's the Mauave limestone below that as well. And even some of the detrital sedimentary rocks. They don't have to be carbonates. Some of the detrital sedimentary rocks, which would include shales and sandstones, many of those also were marine rocks. And so, pretty cool. So the original source for all of these things, well, the clays, had to come from the weathering of igneous minerals, igneous silicate minerals. The sands had to come from the weathering of igneous rocks as well. Out of a granite, you can pull out the granite bits that would decay and form sediments around a granite body, and eventually that material is going to be transported by streams, rounded off. The feldspars and many of the other silicates will turn to clays. The sand stays behind and gets transported even farther and farther, and eventually gets transported long distances away and accumulates there. So that's what you have with the Grand Canyon, is this enormous record of sedimentary rock deposition and then eventually erosion that cuts into it. So what was sedimentary rock has now been eroded away and redeposited somewhere else. It's that reincarnation theme again. In the next slide, so if that was water erosion in the Grand Canyon, if that was water erosion, what we're looking at here is glacial erosion, and you already know that this is an igneous rock body. This is the Sierra Nevadas. The Sierra Nevada batholith was kind of uplifted here, and then the glaciers came in during the last ice age and carved out these really deep valleys like this, and so it left that big, broad, U-shaped valley. It's very different from the sort of valleys that you get with stream erosion. Stream erosion usually leaves a V-shaped valley like this, because the stream's down here at the bottom, and the valley has, and we're going to talk a lot more about, in fact, streams in this course. Streams are intensely, well, everything's intensely interesting to me in geology, but streams make a V-shaped valley, whereas glaciers tend to be broad, and they'll make a broad U-shaped valley. And so that's what you see here. Now, the very bottom of it has sediments in it, of course, and so that kind of fills up part of that U-shaped valley, but it was carved out by glaciers. In the next slide, we're looking at the Sphinx. The Sphinx is, of course, carved by ancient Egyptians. In fact, they predate the pyramids. The Sphinx here is absolutely ancient in age, or roughly around the same age as the pyramids, but maybe a little bit before that. 65 feet high, and for the longest time, they didn't know the Sphinx had paws and a body behind it. It was just a head sticking out of the sand. And so the sands of the Sahara Desert have blown up and covered most of this statue. Well, in fact, what you see here, most of that is not made out of bricks. Now, the very bottom part is where you can see where they've carved limestone bricks and put those back onto that surface. But if you look at the Sphinx's head, you can actually see bedding planes in it. It was carved out of the limestone first. And so they carved this monument in place out of a rock exposure by removing all the rock around it. And so what you see instead here is that carving for the most part, and then later, once they excavated all the sands out and everything, they have replaced some of the bricks that would have been around the lower part of that huge monument. So that's the Sphinx. Wind erosion would have caused much of the upper part to be eroded as it is today. Now, when we talk about this, one of the key things that we look at when you see rocks that are exposed, one of the key things that causes them to weather very commonly is the fractures that cut across them. And so this is a famous example of one of those rocks that is not fractured so much. Now, this rock is about 1 mile by about 1.5 miles, and it sticks out of the desert floor, and it's made out of sandstone, and it is essentially vertical in its orientation, so the beds are vertical in orientation, but that's what kind of gives the shadows in this photograph here. But in fact, there's hardly any fractures. There's a handful of fractures that go through it, But because it's in the desert and there's a lack of water in this situation, it did not erode very rapidly. And it's made out of sandstone and very resistant as well. And so that's called Uluru right there. They used to call it Ayers Rock. And so that crops out in the middle of Australia. And so that is, it's a place in the middle of Australia where, you know, the agents of erosion just don't get to it very easily because it's not very heavily fractured. So if we look at the next slide here, you can see all the beds of sandstone that cut across there. Well, why are they vertical, you might ask? Well, that's because they were involved in a mountain building episode which tilted the rocks vertically from when they were once horizontal. So, but even after that, there's only a few places on this photograph where you can see where water is gently carved, little tiny rills or little tiny valleys in the rock surface. And that's on the bottom part of this image here on the south side of that exposure here. But that's Uluru right here. So there's a handful of fractures across here, but not very many. One of the things I like to do, as you well know, is I like to point out literary references as well. So if you ever get a chance to read a book by Bruce Chapman, he's a great author, travel, and he wrote the book called In Patagonia. He also wrote a book called Songlines. And Songlines is all about how rocks like Uluru and other rocks in the outback, in the deserts of Australia, were used by the native Aboriginal peoples of Australia. The native Australians would travel this landscape, and in order to navigate that space, they actually sang songs which carried tales about the origin of each one of these features like this. So it's an interesting book. So highly recommended, actually. I haven't read it in a lot of years. I've got a couple of copies of it. So much so, well, actually one of them was stolen from me, so I had to buy another copy to replace it. But fascinating sort of reads like that. And so geology and literature can go together like this as well. And geology and travel go together like this as well, too. This is a student field trip we did back in 2008, I think it was. And so these are some of the former students we had. Let's see, that's, I can't remember her first name. That's a Williams there. And my wife is actually in this photograph. She was with us here. And a former professor at Missouri State, that's Dimitri with a do-rag in the background here. That's Zach here in the foreground here. And so, but this is a group of hikers. We went hiking this day when we're on a field trip to the Canadian Rockies, and so this is in the Canadian Rockies. And what you're looking at here is actually a limestone, and it forms the basis for Hauling Peak. This is the peak that is to the west of a city called Kenfield. And if you've heard of Banff, Banff is in Western Canada, one of the most beautiful places on earth. This is a little bit south of Banff, and so we went hiking this day and climbed up the backside of Hauling Peak here. And had this wonderful opportunity. We took a photograph here, but that's a limestone right there. That is a limestone overlooking a big, broad, U-shaped valley that was carved by a glacier. So glaciers not only carve igneous rocks, they can carve sedimentary rocks as well. And in this case, they're carving into what are the Canadian Rockies. And so the Rockies were uplifted also. Not only were they uplifted, but they were also deformed. So these rocks are on and are tilted as well. And you can see how they're kind of tilting and dipping to the west here. So the east is off to the left-hand side, the west to the right. And so as you look on this landscape, those rocks, in fact, were emplaced by a big push from the west. And so when something collided with this area, it pushed all of the rocks, the Canadian rocks, stacked them up essentially, and it pushed this limestone over the top of even younger rocks. Actually, it's a type of fault we call a thrust fault. But anyway, those are carbonate rocks there. Again, limestone rocks. These are Cambrian in age. So if you went into the Grand Canyon, some of the lowest sedimentary rocks in the Grand Canyon would include the Moave limestone. It's roughly the same age as this limestone here. So those are different types of erosion. So you've seen glacial erosion, you've seen wind erosion, you've seen water erosion. Now we're going to talk about the different kinds of sedimentary particles, and we're going to talk specifically about the ones that are detrital sedimentary particles, What detrital means is that it was once detritus. In other words, they were pieces of sand grains, broken pieces of rock that either accumulated from that water processing or it accumulated from the wind blowing it and having it accumulate in sand dunes, or it could have been in like the sand dunes you see here, or it could have been in water ripples and things like that as well, or gravel. Gravel can accumulate in beaches, for instance. We call them shingle beaches, but in this case, gravel is very commonly at the very bottom of mountain streams. And so if you have a mountain stream, very commonly there'll be gravel in it. And so that's what you see at the top here. So these terms that I'm using are very specific, as it turns out. And so when we look at this, we say that gravel could include things that are, like millimeter size or so, bigger than a millimeter, centimeter size. So, about as big as the end of your little finger, let's say, all the way up to things that are boulders or bigger even. So there are even particles that are bigger than that. They don't get moved by wind, but sand does. And so gravel is one category. We like to think about, do you have a good memory for that's gravel? Well, maybe you don't have a good memory of what's the difference between a boulder and a pebble. Well, pebbles are smaller, right? Granules are in between. And so cobble's the next size up before you get to boulder size. And so there's actually a scale by which we measure these things. So it's kind of arbitrary, but that's what we use to describe the sediments. And then we also use it to describe the sedimentary rocks. And so here you can see that there are sand grains in here. And so the sand grains that would form those sand dunes. And then over on the right-hand side, those are silt grains. And there's a way that we can determine what silt is as well. But each one of those varieties, each one of those grain sizes, let's say, is detrital. It's been moved there. It's been sorted in some of these, right? So there's all the same size for some of these grains. Wind is very good for doing that. Water is okay for doing that. And then glaciers are horrible at it. But we'll look at that. Here's the arbitrary chart that we use to describe these sort of grain sizes. At the very top up here, we're talking about something that's 4 meters across. When you go down, you can get to 2 meters. Well, that's all the gravel category. So there are 2 millimeters, 2 millimeters. So the scale over here goes from 2 millimeters, 4 millimeters, 64. They squared it each time, or they made it's a square of 2 essentially. So 8 is 8 times 8, obviously. So each of these are kind of arbitrary. But 2, 4, 64, 256, and 4.096. So that describes the different varieties of gravel. So we have granule, pebble, cobble, and boulder sizes to associate with that. Now this is actually a geology scale. This is not the sort of scale that gets used in industry. Now in industry they use something called the ASTM. It's a standard sort of like scale that we use to describe the grain size, but this is the geologist version of that. And so this is put together by a scientist named Udden first, and then Wentworth came along and re-described these rocks. And so this is the Udden-Wentworth scale. And so if you get 2 millimeters, okay, so 2 millimeters, the size of 2 dimes or a dime and a half stuck together, that little bit right there, that 2 millimeters is the cutoff between what's a sand grain and what's gravel. So gravel's larger than 2 millimeters. Sand grains are smaller than that, all the way down to 1, it's 0.0625, so a 16th of a millimeter, in other words. So a 16th of a millimeter is the cutoff for something being considered to be silt. So sand, we say that those are grains. And for silt, you would say silt particles. And then if you take silt, you can take it all the way down to very fine silt. And below that, we're going to call that clay size. So clay has 2 meanings. Clay is both a size and it's a mineralogy. So the mineralogy would be a silicate. That's usually what they are. And they're usually relatively flat as well, but they're very, very tiny as well. And so clay can mean either the clay minerals that form them, or it can be the grain size. So if those are the grain sizes, okay, and so we have divisions for the sand grain, so you can have coarse sand, medium sand, fine sand, very fine sand, then you go to silt, right? So there's 4 categories of sand. If it's a rock that's made out of sand, let's say it's all been cemented together with silica cement perhaps, which is the most common form, it's going to be a sandstone then. And if you take and cement gravel together, it's usually going to have a matrix of some sort, which may be sandstone in fact. And so gravel very commonly will have other sorts of grain sizes mixed in with it. Usually it's not just the gravel itself. Something fills in those interstitial spaces in between. And so that would be called a conglomerate if they are rounded clasts. And so when we get to 2 millimeters and larger, we call those clasts. And so that would include granules, pebbles, cobbles, and boulders here. And so each one of those, if you were to have a whole bunch of them together and you stuck them together with cement and say there's nothing in between the grains, it's just the cement holding them together, which is really rare. It's not going to happen in nature usually. That would still be considered a conglomerate. It would have no matrix and it would only be cemented together. Not real common. More commonly, you will have sand that fills in those pore spaces around those big clasts. So the big clasts all are stuck together in a sandstone. And that you would call a conglomerate with a sandstone matrix. And so the matrix is the interstitial material, the stuff that fills in around the clast. And it could be cement, right? So there could be cement in there as well. So a conglomerate has rounded clasts, a breccia has angular clasts, and then sandstone, of course, is just the sand grains size themselves. Usually they're much more well sorted, so you're not going to get too many pieces of gravel in it. And then eventually you get to siltstone and then claystone. We're going to look at examples of each one of these. So for right now, I'm going to call it right there, and we're going to get deeper into sedimentary rocks as we go here. So the Udden-Wentworth scale is where we close, and now we're going to look some examples of each one of these detrital sedimentary rocks. Talk to you in a minute. Bye now.